Um, okay, so welcome everyone to our second tutorial today, the tutorial on LP-based heuristics for cost-optimal classical planning. So I am still Malte Helmert. I'm on the right of the picture now. This will be co-presented with Florian Pommerening sitting over there and Gabriele Röger sitting over there. Of course, if you have any questions, we're more than happy to answer them right away. Actually, I have a feeling that at least the parts I'll be talking about won't need all the time we've allocated to it, and also I think we can add at least 1 hour to the schedule at the end because some of the workshops run that long, right? We're not planning to do that, but you know, if you have questions, just ask. And of course, if you have questions coming up later, then email us. Also on our web pages, we want to put up these slides and also an annotated bibliography that I'm not sure if we can go over the bibliography here. It depends a bit on the timing, but it will be on the web. Okay, so this looks similar to a slide if you attended the previous tutorial we had there. It's slightly different, but what we really don't want to do is talk in detail about what planning is. But I hope most of you know that. So who among you knows what strips is, what SAS plus is, what A star is, and what admissible heuristics are? That seems to be almost everyone. That's very good. And it will be useful in certain cases to be familiar with kind of major concepts that underlie the common heuristics commonly used in planning, especially for the parts where we'll try to make some connections between these. So you won't need this necessarily to understand what we're doing here, but it may be interesting to know a bit about these things to kind of understand kind of why these things might be interesting, the connections, how this relates to other things we've been doing. I won't ask you if you know what abstraction is, because if you don't, it's your own fault. We just gave a tutorial on it. But who knows what landmarks are in planning? Okay, there's still most people. That's very good. Who knows what delete relaxation is? Okay. Actually, we only have like slight connections to delete relaxations here and there, but you might get a bit more out of it if you know about that. Okay. So let's maybe start by explaining the title, because that's also the motivation for the talk. So this is about classical planning. So we have a large state space which is specified in some kind of declarative specification, in our case, as a SAS plus planning task. And in that state space, we want to find a path from the initial to the goal to some goal state. It should be cost optimal here. So we really want to minimize the cost of this path, which is defined as the sum of costs of the actions along the path. And the way we want to do this is by heuristic search. You know what that is. And in particular, we'll be interested, and this is the real focus of the tutorial, techniques using linear programming. So LP stands for linear programming, and we'll use linear programming to come up with the cost estimates. Now, you notice on the previous slide, I didn't say we assume you know a lot about linear programming. That's not part of the assumed background. Rather, we'll tell you a little bit about it, but only really a little bit, because you don't really have to know much about it. Here it's kind of really just a black box thing that we will use. So a linear program, or LP, we'll often use the abbreviation, is basically a set of constraints with something else on top. So we have a finite set of variables, like in mathematics, that can take on real values, like 3.2 minus 7. We have linear inequalities over these variables. And we have an objective function, which is a linear combination of these variables that we want to optimize. Optimize means either minimize or maximize. So we'll be looking for assignments to these sets of variables that satisfy all these constraints. So these would be called feasible solutions. And among those, we want those that achieve a particularly high or particularly low value according to the objective function. And that's most easily understood with an example that you'll see in a second. Before we get to the example, one more thing is that sometimes we're not considering real values here, arbitrary values, but integers. That's then called integer programming. And everything else is the same, only you can't have fractional values, and that makes the problem much harder. We talk about that in a second. Here's an example of, well, either an LP or an IP. It doesn't actually say whether these should be integers or real numbers. So this is like a typical example. We have variables x, y, z. We have these constraints. If you want, you can also view these as constraints, or kind of, some people just say, well, this kind of particular type of variables, non-negative variables. And there's many ways, of course, to satisfy these constraints. For example, you can set everything to 0, but we don't want any odd solution. We want a solution that maximizes this expression. And if you look at this carefully, you see, for example, that it doesn't really make any sense to set y to any value other than 0. because it will only make this constraint less true and worsen your objective function. So let's set y to 0. Once you've done that, you see that having more of x is better than having more of z, because x occurs with a higher coefficient up there. So let's make x as high as possible. Well, the highest possible value of x that achieves these two inequalities is actually setting x to 5 and z to 5. So that's actually the optimal solution here. And the objective value associated with that would be 15, because that's 2 times 5 minus 3 times 0 plus 5. And of course, we are not the ones who are going to solve these things. The computer is going to solve these things. And they can do this reasonably well, especially if we don't require integer variables. In particular, this is a polynomial time problem. So you can easily have, well, at least a few thousand variables and constraints and expect this to be solved in time. That can be really something that you can do many times in a large algorithm, for example, like evaluation of a state in heuristic search. You won't perhaps be able to do that if you insist on having integer solutions, because that's an NP-complete problem. Doesn't mean you can't solve it, but it does mean, of course, you can't scale to the same sizes, or you can't solve it as often as you might be able to do with the linear version. So what you often do is, what you really care about is an integer problem, but you don't actually need an exact solution. Maybe you just need some kind of approximation for the best for the best objective value. Is you just take your IP and treat it as if it was a linear program. That's called LP relaxation. You have, of course, to be careful if you're using this for heuristics, for example, if that actually preserves admissibility, and that depends on the context, whether in your case it kind of makes your heuristic worse if you use a LP relaxation, or whether it makes it inadmissible potentially. So that's actually one of the things that kind of in the background will be important for quite a few of the results we present. Okay, so we don't really need much theory about linear programs, but there's one thing, I guess, that you should know about. Most people probably do know about it already, but it's worth emphasizing because it occurs in quite a few contexts. So if you have a linear program, you can kind of do a mechanical transformation of it into another linear program called the dual of the original one. And in a certain way, well, in a very direct way, but one that for non-experts really, or people who kind of trying to get to grips with this like me, is kind of hard to understand intuitively, but in some odd way, the variables become constraints and the constraints become variables. So that's what dualization does. And if you have an LP that has an optimal solution, so it's feasible, it has a solution, and also it doesn't have solutions that are unbounded, you can't push the objective value as high as you like. So in LPs of this kind, it's guaranteed that the dual has exactly the same objective value. So that means you can actually solve your LP by solving the dual instead. And one more thing, so the original problem is a maximization problem, the dual is a minimization problem. This is useful in quite a few cases where you, for example, have an integer problem and you kind of, if you LP relax it, you would bound it kind of from the wrong direction. There are sometimes tricks you can play using the duals instead, kind of to get an approximation from the right direction. Okay, said that already. If you call it a dual, and if you know what a dual is in another context, you would kind of expect that the dual is kind of a self-inverse operation. So if you take a dual and dualize it again, you get back the thing you started from, and that's indeed the case. So the dual of the dual is the original linear program. Okay, that's, I think, all we really need to know about it, unless we want to go really into the proofs of the things we present, and we don't want to do that. So for the rest of this introductory section, I basically give you something like a table of contents. I talk about the 3 key ideas that we want to talk about in the next hour and a bit. And yeah, let me maybe just get started and say a little bit more about them a bit later. So one of them is something that people in planning, I think, have known for quite a while, at least for 7-8 years, but it becomes quite a bit, it gets some new interest in the context of the LPs we're talking about, and that's cost partitioning. So the idea of cost partitioning is you have a planning task you want to solve, and you create a bunch of copies of it, basically. So you have one planning task, and you kind of turn it into 5 planning tasks that are all the same as the original one, but then you modify it a bit. Basically, what you do is you change the cost function of each of the copies. So you have the same problem, but with like lots of different cost functions. And you impose a constraint, namely, if you look at like one particular operator and the cost that you assign to the operator in each of your copies, then it cannot sum to more than the original cost. So if it costs 10 and you split it in 3 problems, in 3 copies, one thing you can do is assign costs of 7, 3, and 7, 7, 3, and 0. That's fine. That sums to 10. you couldn't do 7, 4, and 2. That would be too much, right? So you have to satisfy this constraint. But apart from that, you can do what you want. And the nice thing about this is that you can then independently compute a solution or even just an admissible heuristic for each of your copies, sum them up, and get an admissible heuristic for your overall problem. And kind of the underlying idea, well, I shouldn't say more about that because we'll go into detail about that. So that's what cost partitioning is. Create your copies, distribute your costs, gives you an admissible heuristic. What it is a very, very generic, very powerful method for obtaining additive admissible heuristics, right? You're not using any properties of the problem here, really, other than the fact that there are somehow additive costs involved. Actually, it's applicable to things completely unrelated to planning, like many combinatorial optimization problems. The second key idea, and that's more recent, that's something that started like a few years back, maybe like 2 years ago, is so-called operator counting constraints. So these are linear constraints in linear programs of like we've just seen. With a particular semantics, it's constraints that talk about how many occurrences of a given operator you're going to need in a plan. So let's say you have a problem, you want to solve this problem, and you can find out some properties of the problem by doing a bit of analysis. Like, for example, I'm going to need operator 1 at some point, or I'm going to need operator 2 at some point. I know this. Then you can write this down as a numerical constraint that says the number of occurrences of O1 plus the number of occurrences of O2 must be at least 1. And that's an operator counting constraint, a linear constraint on these kinds of variables. But you can express very different things. For example, this one would express that you cannot use O1 more often than O3, right? Because if you move YO3 to the other side, it says YO1 less equal to YO3. So the semantics of that is supposed to be, in every plan, I know that O1 cannot be used more often than O3. If you have that information, that's how you can write it down as an operator counting constraint. Why is that interesting? Because then you have the information you want to use written down in a declarative way, and you can do with that what you want. You can kind of feed it to algorithms that give you derived constraints or whatever you want. So it's a declarative way of representing knowledge, and if you're into AI, this is always a nice thing because then you can start reasoning about things. And that will be a major focus of the presentation. Now the third thing and the final thing are so-called potential heuristics. It's kind of the most recent of these ideas. It might sound a bit unrelated at first. So let's look at what it says here. So the idea is we define certain numerical features of states, like functions that we can apply to a state and give us a number. For example, I don't know how many. Let's say I have some kind of logistics problem. How many trucks are there in location X? That's a state feature. I put a state in, I get a number out of it. Okay, let's say we define some of these, and then we say, well, I want to come up with a good heuristic that is based on these state features. Namely, I want a heuristic that is a linear combination of these state features. I don't know, what the weight should be, but I like these linear combinations because, for example, these are the things that have been very, very popular in game playing, and they're efficiently computable. The features are efficiently computable, so they kind of look nice. We just ask ourselves, okay, what kind of things can you do with that? And basically, what we will study in this part of the presentation is approaches for kind of studying these kinds of heuristics in a way that kind of the difficulty of coming up with heuristic, of actually tuning it in a way that you come up with something that gives you a good heuristic value and is admissible and consistent. And so it's not done by you anymore. It's done by some kind of optimization process. So it's a declarative approach for designing heuristics. And because heuristics are linear combinations, they're actually also fast to compute, at least if the features we use are fast to compute. So, of course, well, hopefully, if this is a good presentation, these are not just 3 things that have nothing to do with each other, right? So kind of the punchline will be that everything seems to somehow be connected to everything else. And that's what we will hopefully convince you of in the following 3 parts, which basically deal with these 3 things in sequence. So the first thing we'll talk about now is the cost partitioning, and that part will be done by Gabi.
Okay, let's first have a look again at the slide on cost partitioning we had previously. So what we want to do is we want to distribute the operator costs among a set of copies of planning task of a planning task, and then the sum of the optimal goal distances will be an admissible estimate for the original optimal goal distance. And of course, we usually don't work with optimal goal distances, but use admissible heuristics to get lower bounds for these. And for like and such admissible heuristics, the sum of their estimates, always computed on their respective copy with the adapted costs, will be an admissible estimate for the original task. The question is this always good? Is it always bad? And the punchline is it can be better or it can be really, really worse, and that depends really on the cost partitioning we choose. And there are many different strategies for defining cost partitionings. The simplest one, which often also works very well, is the uniform cost partitioning, where we just distribute the operator costs equally among the copies of the tasks. There's 0-1 cost partitioning, where just sometimes we know that in some heuristic won't make use of any operator cost, so then we give it 0 and distribute it equally among the others, or in the extreme case, one copy gets the full operator cost from an operator, all the others, the operator will be free of cost. And the question is now whether we can do really, really well, so whether we can find an optimal cost partitioning. And that's the main part of this section on cost partitioning, because this is where the LPs come into the play. We can use optimal cost partitioning. We can define optimal cost partitioning when we can express the heuristic values of these sub-heuristics with linear constraints. In this case, we use variables for the cost of each operator in each copy, define the heuristic estimates as with these linear constraints, and simply optimize the cost partitioning, on our estimate from the additive heuristic then, by maximizing the sum of heuristics as the objective function of our LP. And, well, as I said, we need to know, we need to have a possibility to define a heuristic as with linear constraints, and this is already known for abstraction heuristics and for landmark heuristics. So I will show these as examples. So everyone should know abstractions by now from the previous tutorial. If you don't, abstractions are just simplified versions of planning tasks, for example, projections. And the important thing is that the cost of an optimal abstract plan is the admissible estimate of this abstraction heuristic. So if we want to express the heuristic value as a linear constraint, we need to kind of formulate the cost of optimal abstract plans. And this is a solved problem, because it's just the shortest path problem in the abstract transition system. So where we really talk about individual states, or individual abstract states, and individual transitions. So for the moment, just consider a standard state space without copy, abstraction, cost partitioning, anything. Just we have given a state space, and we can compute the optimal goal distance with this linear program. We have variables. First one for the value we really want to compute, the goal distance. And then we have a variable distance s for each state in the state space. And this is the distance, the shortest distance from, or should capture the shortest distance from the initial state to this state s. And we want to maximize the goal distance. That looks odd at the first thing, because we want to find the minimal goal distance, but after the constraint, I think it becomes more clear. Let's first have a look at the distance variables. So of course, we know the distance for the initial state should be 0. That's what this first constraint says. And for all others, that's where the minimization comes into the LP. If we have a transition from a state S to a state S prime with operator O, then we know that S prime can't be further away from the initial state than S is away plus the cost of this operator, of this transition. So since we have this constraint for all transitions, this kind of minimizes us the distance variables. And we want to choose, or we want to have the smallest goal distance of any goal state. So for all goal states, we say that our goal variable, or our objective variable, must be at most as high as the goal state is away from the initial state. We want to maximize this, so this way we get the actual optimal goal distance. And from this to the optimal cost partitioning for abstractions, it's not very far. What we do is we compute this for every copy, for every abstraction. So we will here have abstractions alpha. For each of these abstractions, we have a distance and a goal dist variable as before. But now we also make these the operator costs variable. So previously, now it went down. Previously, the operator costs were given, but now they are flexible. So what we see here, that's just what we had before, everything copied for a specific abstraction. But now we don't have the fixed given operator cost here anymore, but a variable, which does the cost partitioning. And that this works properly is done with these constraints. This is just the condition that it's actually a cost partitioning. The sum may not exceed the original cost, and each operator cost must be non-negative. And with this LP, we can really compute the optimal cost partitioning for any abstraction, for a set of abstraction heuristics. Okay, the second example are landmarks, especially disjunctive action landmarks. These are sets of operators of which we know that every plan must contain at least one, and we assume that we have a set of such disjunctive action landmarks, and want to optimize the heuristic estimate we can get out of them. And the landmark cost is just the cost of the cheapest operator. So for each landmark we know we need to apply at least one operator of these. So we know we have at least to spend the cost of the cheapest one. And if we want to see this in the lens of our copy of tasks, we have very odd copies where the goal is just apply one of the operators given in the landmark, and several of these tasks. And now we can do the same thing again. This is like the flavor of the originally introduced optimal cost partitioning for landmarks, which is a maximization problem, as we had before, where I said we maximize the sum of the heuristic values and optimize for that. But I find the intuition behind this is not as easy to see, so I don't want to explain it in detail, but instead want to show you the dual perspective with the dual LP, which is much easier to grasp. So what we now have, swapping variables and constraints, we get variables occurrences O for each operator, and you can think of this, that's just the number of occurrences of operator O in a plan. And now we want to minimize the plan cost, because we want to get a lower bound on the actual plan cost, and the plan cost is just the cost of an operator multiplied with the number of occurrences of an operator summed up over all operators. And now it becomes really clear how the landmarks get into the LP formalization. If we have a landmark L, we just know that the sum of all operator occurrences of this operator must be at least one, because we must apply at least one of these operator. And we also know that in a plan, each operator cannot occur negatively often, so it must be at least 0. So in this way, we can really get the best heuristic estimate out of a set of disjunctive action landmarks. Nevertheless, so the best heuristic estimate sounds great. What I let a little bit implicit is that these LPs depend on individual states. So the set of landmarks usually depends on a state, and also the abstraction optimization depended on a specific initial state. And whereas this optimization gives us the best possible cost partitioning for the state, its computation can be very costly. And the better heuristic estimates do not always outweigh the additional overhead for computing it. So especially for the abstraction, so if you think of pattern databases, you usually pre-compute them once. You usually pre-compute them once, and then you just look up, doesn't jump anymore, look up the values from a hash table, but with this optimization, you can't do this anymore. you really have, whenever you compute this, you resolve the entire abstract systems again and again and again in every state, which is very costly. So it does not always pay off. But it's very interesting because it helps you checking the power of things, what would really the best we could get if you want to compare to other methods. What you also could do is optimize now or then and reuse the cost partitioning you get several steps. Okay, so far to the optimization. The next thing I want to show you, which is pretty new, I think we only published it this year, is general cost partitioning. So usually cost functions are non-negative in planning tasks, so that's intuitively clear. And I also kind of sneaked this in from between my and Malte's slides in the definition of cost partitioning. And here, where I previously showed this, I added this, okay, cost functions to the non-negative reals. And what we want to do now is to loosen this restriction. We want to allow general reals. So in the copies, the operator cost can also be negative. Does it make sense? Well, at the first, intuitively would say, no, why should we do that? That doesn't make sense. Cost functions are non-negative. But we can show that for the cost partitioning for this large theorem that we get an additive heuristic, it is actually not necessary. And I will now show you by means of an example that we can actually improve with this general operator cost partitioning. So here is an example that's a very, very small state space with a red action and a blue action. And we have two abstractions for it, projections on the second and on the first variables, and assume that each, so the red and black action both cost 1. And since in this projection all states are goal states, we can't really get a heuristic estimate out of that because we always get heuristic estimate 0 from that. So we can use all of the cost of the blue action in this abstraction. So we would assign blue a cost of 1 here and here 0, and for the red action it doesn't really matter, and get a heuristic value 0 from here, 1 from here, so a total heuristic value of 1. Now assume that we can also use negative action costs in our copies. So for example here, we still ignore the, or kind of ignore the red cost. What we do here is now we have a negative action cost for the blue action in this abstraction. Which means that for this goal state we would still get an estimate of 0, but for this goal state we would get a heuristic estimate of -1. Because we can reach a goal state with cost -1, which is smaller than 0, which is when we do nothing. So here we have a heuristic estimate for the initial state here of 0. But what happens in this other abstraction? Here we can use the cost we reduced here and assign the blue action a cost 2. And now we get a heuristic estimate of 2 from this abstraction. So for this initial state we get a heuristic value of 2, which is better than the one we get previously, which was the best we could get with non-negative operator cost partitioning. So this can be really, really beneficial. And question is, or often question is when we present this, well, can't you go on like this and go on and go on and go on, make this more negative and more negative and more negative and add this up there? And it's easy to show by the example that it's not a good strategy to do that, because as soon as we go to -2 here, we have a cycle of negative cost. So we get a heuristic estimate of -infinity from this abstraction, and of course can't make it up here. So there's still some optimum. And that's what we call general cost partitioning. It's strictly more powerful than what we call non-negative cost partitioning, what we previously always had. Of course, we can also compute an optimal general cost partitioning as we did before, mainly by omitting the constraint that the cost variables must be non-negative. And since omitting constraints can only improve the heuristic estimate. This can only improve the objective value. This can just improve the heuristic estimate. And in the next section, we will see that with this general cost partitioning, we get very, very interesting connections to the operator counting framework. And that will be presented by Florian.
Okay, so I'm going to talk about operator counting. Here's a reminder, the slide that Malte showed before. The main idea is we want to have linear constraints over the variables that count how often an operator occurs. So let me show a slight example of the way this can make sense. So imagine you have the space of all possible operator sequences, just every possible way to order sequence, whether it's applicable or not. And now, instead of having all of these sequences, you forget about the order of operators and just consider how often each operator occurs. So for example, this tuple up here would mean that you have, of 3 operators, you apply the first one twice, the second one only once, and you don't use the third one. And now if someone tells you a property that all plans must have, like you need to use the third operator, you need to use operator C at least once, or A and B together have at least cost 4, or when you use A, when you use C, you must use A at least once more. Now, when all of these are actual properties of plans, so every plan must satisfy them, then you know that the tuples that represent plans must be in the intersection, must be in this area here where all of the constraints are satisfied. And now, when we are not looking for an actual plan, but we're just looking for an admissible estimate, we can actually look for the cheapest element within this set. So in this case, assuming all operators cost 1, the cheapest one is using the first 2 operators twice and the third operator once for a total cost of 4. So to be a bit more formal, this is the general framework of operator counting, of an operator counting heuristic. We want to minimize the total plan cost. So that is, for each operator, the cost of the operator times the number of times it is used. And we want to minimize this total cost subject to the restriction that we can't use an operator a negative number of times, and subject to some operator counting constraints. And these operator counting constraints, as Malte already said, must be a set of linear inequalities, and we have to have one property that actually connects them to the planning problem, because otherwise we could just write any linear inequality and we could basically derive any estimate we wanted. So the property that connects them to the planning problem is that whenever we have an actual plan to the solution, so an actual plan to the problem, then there has to be a solution to the constraint, so a way to set the LP variables where you set all the operator counting variables, these YO, to the number of times this operator occurs in this particular solution. So for every possible solution, you have to find a way to satisfy these constraints, these inequalities, with the actual occurrences of this operator in this plan. So the 3 main properties of operator counting heuristics are, first of all, these are admissible. And this is whether we consider the integer program or the linear program. So the integer program has the additional restriction that you can't use an operator 1.5 times. You have to use it an integral number of times. Of course, it is harder to solve. So the LP heuristic, the LP operator counting heuristic, is can be solved in polynomial time. The integer problem of this cannot necessarily be solved in this time, but there's some work on using the integer program as well. Next property is, Gabi just said, when we drop constraints, we increase the heuristic value, which is true for a maximization. So if you have a maximization and you drop constraints, the value of the linear program can only increase. But here we're talking about a minimization. So in this case, if we add constraints, the objective value of the linear program can only increase. So whatever constraints we add, as long as they are operator counting constraints, they can only make the heuristic more informed. They can only add information to the heuristic. And this is a very interesting property for heuristic combination. So if we have two operator counting heuristics, both of them have a set of constraints, a set of operator counting constraints. We can just put all of these operator counting constraints together into one linear program and solve this linear program with the same objective function as before. This combined linear program will also be an operator counting heuristic. And as I just said, adding constraints can only increase the value. So this combination of both of these heuristics has to have at least the value of each of the individual heuristics. So it dominates both of them. It could be that it just always maps to the maximum of both heuristics. But in fact, it can also have a larger value. So there can be a positive interaction between the constraints from different heuristic. And that actually happens in practice. So this is a plot of expansions that happened in A-star search using the maximum of two operator counting heuristics here on the x-axis, on the y-axis, and the combination of two operator counting heuristics into one linear program on the x-axis. And as you can see, there are tasks where we actually save an exponential number of expansions. So the heuristic quality can get much larger, or can get so much larger that we actually save a lot of expansions. And this is just by interaction between the constraints. So I now want to go through 4 examples of heuristics that we already know can be expressed as operator counting constraints. And the first one is something we've already seen, which is disjunctive action landmarks. So the last formalization that Gabi showed already had the form that we need for operator counting constraints, which is the sum that just says we need to use at least one operator from this set. So we know that if we add all of these constraints for a collection of landmarks and optimize this for a minimal total plan cost, the result will be the optimal cost partitioning for landmarks. And this is not a coincidence, this connection to cost partitioning, but I will come back to this later. For now, I want to go to the second example, which is the post-hoc optimization heuristic, which is based on the simple idea that if you have a heuristic, not all operators might be relevant to this heuristic. So there might be operators where it doesn't matter what cost they have, the heuristic will always be admissible. Think about a projection where you project the whole planning task to one variable. And if you have an operator that doesn't mention this variable, then it doesn't actually matter what cost it has. The heuristic that you compute, the heuristic value is still admissible. And admissible in this case means that the heuristic value must be a lower bound to the cost of the operators of any plan. And since these irrelevant operators are not interesting in this case, we can just drop them. And we can instead say the heuristic value must be a lower bound for the cost induced by the relevant operators. So the cost induced by the relevant operators is just the number of times each relevant operator is used times its cost. And this is an operator counting constraint. So for the third example, I want to talk about the state equation heuristic, which is known by different names. It was originally introduced in 2007 as an order relaxation heuristics, that did not consider the order, so similar to delete relaxation that does not consider delete effects. Order relaxations drop the order, which is similar to the idea of operator counting. Then in 2013, Bly-Bonnet kind of rediscovered it via a different way, through a different idea as a property of Petri nets, and called it the state equation heuristic. And in 2014, both of them wrote a paper on extending this idea to flow-based heuristics. All of these have in common that they are based on the idea that effect in the planning problem can be either produced or consumed by an operator. And with produced, I don't mean that this is an effect. It's true after the operator is applied. It's more strict than that. I mean, an effect is produced if it is made true. So if it was false before and if afterwards it is true. And consumed is the same thing. An operator consumes effect if the effect is true before and if false afterwards. And the idea of these heuristics is that if you consider a complete plan, the total number of producing and consuming operators must balance out. So formally, if you consider all operators that have this effect as an effect, and all operators that have an effect as a precondition, the number of times you use such an operator must balance out to 0. And this is not true in every case, so we have to take care of the goal state and the initial state. In the goal state, we have to allow one more producer because we actually want to produce the goal value. So we add 1 in for goal states. And for the initial state, we allow to consume the value once more than we produce it. So we reduce the total change by 1. And what I've shown here is a slightly simplified version of the task, because there can be operators where you're not sure whether they produce or consume an operator. So think about an operator that has an effect on a variable but doesn't have a precondition on the variable. Then you know that the effect is true after applying the operator, but you don't know whether it was true, was already true before. And in this case, the operator wouldn't produce this. So there is a way to write this down in general. It's slightly more complicated, and I didn't want to put it on the slide here. The interesting thing here is that we can actually write this down like this if we assume that the task is in a special form. It's in a form where every operator mentions the same variables in its precondition and in its effect. Then this special case I was talking about just doesn't occur. And one interesting result is that this is not a restriction, not a limitation, because we can transform any task in this form without blowing it up, without making it exponentially larger. And that's actually something I will talk about on Tuesday in the first afternoon session. And maybe I should mention this too here. If you think about the general form of these constraints and the transformation in normal form of a general task, you will end up with the same constraint. So the kind of constraint actually, the heuristic that is computed is actually the same. Okay, before I go to the last example, I want to say one more thing about the state equation heuristic. And that is about cases where the state equation heuristic doesn't capture the information of the planning task, so where it makes errors. These errors are caused because are based on the fact that the state equation heuristic only considers one constraint perfect. And there is interaction between these constraints, but it is limited. So the interaction that you can capture between different variables is very limited in the state equation heuristic. And one solution to that is something called fluent merging, where you consider tuples of facts as a new fact. So you introduce new facts that represent a tuple of your original facts, and then you consider what operators produce this tuple and what operators consume this tuple. And for these operators, you can actually add a new net change constraint, so the type of constraint we've just seen. And again, Menkes, Van den Briel, and Bleibanner did this in 2014 in the flow-based heuristics. What they call dynamic merging actually tries to not merge everything at the same time, but only merge the things that are required. So they repeatedly remove an inaccuracy from the LP solution by merging facts. And then these new facts that they generate by fluent merging lead to new constraints, which make the linear program more restricted, which might lead to a new LP solution. And they repeat this process until the solution they find with the linear program doesn't contain any operators anymore that have this type of inaccuracy. So it's a fixed point iteration. So for my last example, I want to talk about delete relaxation, about relaxed planning. You probably know this, but the delete relaxation ignores all delete effects, which also means that if you apply an operator the second time, it doesn't give you any new facts. So everything that the operator makes true, it already made true the first time you applied it, and it couldn't have been made false in between. So it's never useful to apply an operator twice. And this property means that delete relaxation can actually be expressed as operator counting. And the way this is done is to use binary variables to express whether an operator is part of the solution or not. We only need binary variables here because we don't need to count how often an operator is used, because it there's no reason to use it more than once. But we can connect these binary variables to operator counts by adding additional constraints that just say if the operator is used at all, then the count must be at least 1. So we can express this with the less than or equal. So I don't want to go into detail about this formalization because it takes a few constraints. It's not that complicated, but it takes about 5 different types of constraints. The only thing I want to say about this is that this uses time steps. So it has time step variables, and it works with first achievers. So it says something like this operator is used at this time to make this fact true for the first time. So it's not a general expression of all the things that happen. So you don't say, okay, and then this operator makes it true another time, and then this operator makes it true another time. It just talks about the first time a fact is made true. Okay, so what does this have to do with cost partitioning? There were a few hints already that this has connection with cost partitioning, and I'm just going to come out with the main theoretical result here, which is that combining operator counting heuristics into one LP is equivalent to computing the optimal general cost partitioning of these heuristics. So what does it mean? If you have different operator counting heuristics, each of those comes with its own set of operator counting constraints. And as I said, you can combine these operator counting constraints by just taking them all together in one large linear program and solve this linear program, optimize this linear program. And the result will dominate all of these component heuristics, might be larger. So this result says, if you do this, the resulting value, the value you get, the optimal value you get for the combined linear program is the same value that you would get if you would use optimal general cost partitioning, so with negative costs, for the individual component heuristics. And this theorem can be used in different ways. So one obvious way to use it is to actually compute optimal cost partitionings of heuristics. So if you have different heuristics that you can express as operator counting heuristics, you can put them all into one LP, and you know that what you're solving is the optimal general cost partitioning. In fact, the linear program in this case can be more compact. So, for example, for projection heuristics to single variables, the optimal general cost partitioning uses one variable for each operator and each subproblem. So for each combination of operator and subproblem. We will see in a second that using one LP to compute this uses much fewer variables, and the reason why it can do this and still compute the same value is because of variable elimination. So there are a few variables that turn out to be unnecessary in the direct formalization as a general cost partitioning, and these kind of can be eliminated because well, they are not needed. They are additional information that just states the same constraints in a different way. So the second kind of result that we get out of the theorem is that there is a heuristic that actually has a better or potentially better value than general optimal cost partitioning. So again, we have something better than optimal cost partitioning, which sounds a bit weird, but if we have the integer programming heuristic, this is something that dominates the linear programming heuristic. And you can think of this as the general optimal cost partitioning with the additional constraint that operators cannot be used a fractional number of times. So you also want that you can only use an operator an integral number of times. And again, since this is minimization, adding constraints like this can only increase the heuristic value. But of course, this heuristic might be better than, but it is not guaranteed to be polynomial computable. So it probably will take longer to compute this value. Now, as a third way, and in my opinion, the most interesting way to use this theorem is to analyze existing heuristics and see what they actually compute. So we start with an operator counting heuristic, and we want to figure out what it is a cost partitioning of. So we are trying to find these component heuristics. And we can do this in general with 3 steps. So an operator counting heuristic has a number of linear inequalities. And we can group those into operator counting constraints. So we can basically consider any group of those as one operator counting constraint. And then we have to figure out what heuristic is computed by each individual operator counting constraint, so by each group of these constraints. And once we have figured this out, we know by the theorem that the original operator counting heuristic is a general optimal cost partitioning of these component heuristics. And I'm going to make an example here using the state equation heuristic. So the state equation heuristic has one constraint for each fact in the planning problem, but we are not grouping together individual facts, but we are going to group together a whole group of these constraints, namely all constraints that talk about one variable. So we're talking about all different values of a variable can have. And we are considering all of them as one operator counting constraint. And now we're trying to figure out what heuristic would an operator counting heuristic with only this one operator counting constraint compute. So we are still minimizing a total cost. We are minimizing it subject to constraints that say, for this one variable, I have to respect incoming and outgoing flow in all values. So what this means is, if I consider just the transition system of this one variable, the flow from the initial value of the variable to the goal value of the variable must be must make sense. So the incoming flow and the outgoing flow of each value must balance out. So this is one very typical formalization of a shortest path problem with linear programs. So what we're actually computing here, if we just looking at one variable, is the shortest path in the projection to this variable. So this is a projection heuristic to an atomic, to one variable, to single variable. Which also means by the theorem that the state equation heuristic is the general optimal cost partitioning of all atomic projection heuristics. And this is quite interesting because when the state equation heuristic was introduced, we weren't sure whether in which category of heuristic it falls. So as you might know, there's 4 categories of heuristics, and most or all of heuristics that were proposed so far fall into these categories. This is landmarks, abstractions, critical path heuristics, and delete relaxations. And the state equation heuristics seem to be something new, seem to be something outside of this categorization. But with this result, you can see that the state equation heuristic actually is an abstraction heuristic because it's a cost partitioning of projection heuristics. So what about the rest of our examples? The first one we've already seen. We have seen that landmark constraints are cost partitionings of these individual landmark heuristics that just talk about one landmark. So where each heuristic just talks about one landmark. With this result, we can also see that it's the general optimal cost partitioning, which means that for these individual landmarks heuristics, it doesn't make a difference whether we allow negative costs or not. So if we consider only landmark heuristics, we cannot actually gain anything by allowing negative costs. For the next one, the post hoc optimization heuristic, the answer might seem a bit weird. It's a general optimal cost partitioning of heuristics that are guaranteed to spend a certain amount of cost on the relevant operators. So each component heuristic says that on my relevant operators, I want to spend at least this cost. And this is kind of similar to landmarks. It's not exactly the same, but it's related to landmarks. So a landmark says, from this set of operators, I need to use at least one. And these heuristics say, from this set of operators, I need to spend at least this amount of cost on them. Also, another result that has nothing to do with theorem we've just seen is that the post hoc optimization heuristic is a cost partitioning, not necessarily the general optimal cost partitioning, but it's a cost partitioning also over atomic projection heuristics. And this cost partitioning here is optimal under certain additional restrictions, namely the costs in each of the projections don't scaled completely independently, but instead there is one factor for each projection, and the costs of all operators are multiplied by that factor. So for example, if you consider the first variable, every operator just costs 1/2 of its original cost. And if you consider the second, it costs 1/4 or something like that. And under these additional restrictions, this cost partitioning would be optimal. Which also means that it's in general it's worse it can't be better than the general optimal cost partitioning. So this heuristic is dominated by the state equation heuristic. And finally, for the relaxed planning heuristic, it is still unclear. You could probably see this as a cost partitioning, but it's not clear how to group the constraints. So I mentioned before that you can group any set of inequalities into one operator counting constraint. This is not quite true because if you use additional variables that are not operator counts, these cannot transport information between different operator counting constraints. So if there are additional variables, they should all be in one component, because otherwise the components would be dependent on each other in a way that has nothing to do with operator counts, yeah, well, that's it's not allowed for an operator counting constraint. So for the relaxation heuristic, it is unclear how to group these things into into individual groups of operator counting constraints, because the variables that depend on time steps kind of tie everything together. And it's hard to find ways to cut this into parts. Okay, just one last thing. So far, we have used operator counts in a very specific setting. We've set up one LP. In case of dynamic merging, this might mean solving several LPs until we find a fixed point. But in the end, we have one linear program. We solve it for each state we encounter during a search. And then we use the estimated plan cost as an admissible heuristic. And then we discard everything we've done so far. But the things we are discarding actually carry important information. So in particular, we have these variables for operator counts that estimate how often we need to use an operator. And these variables, this estimation is something that we can actually use. And there is a paper on this ICAPS by Toby Davis and his colleagues, which tries to do this by solving an operator counting heuristic and then trying to sequence the resulting operator counts. So I have had the example before of an operator count where the first operator was used 2 times, the second operator was used 1 time. And there's only so many ways you can build a sequence of this, and you can try if there is a possible sequence that can be applied. If there is, then you're basically done, because the cost of the sequence will match the your admissible estimate, so it has to be optimal. If this is not if this is not possible, then the way they solve it can generate new constraints for the operator counting heuristic, which you can plug back into the operator counting heuristic, solve this again, and repeat this until you find an optimal plan. And this paper got the best paper award, this ICAPS, and the talk is also on Tuesday, so I highly recommend going to that talk and listening to that presentation. So for the last part, Malte will take over again and talk about potential heuristics.
Okay, as you can see, this is the last part. We're also quite well on time, so if you have any questions, put up your hand at any time, or maybe if it's a more global thing after this, because there'll be more connections, so some of the questions might already be answered at that point. Okay, so oops, what did I do? Okay, right. So this is what I showed you in the introductory section, right? This was a slide on potential heuristics. So taking a step back, forget for the moment everything we talked about so far. This is a new approach for designing heuristics. The basic idea is we define some state features, so functions into which you can feed a state. It gives you a number. And you want a heuristic that is a linear combination of these. Okay, how do we find a good heuristic that looks like this? That's kind of what we want to talk about. And basically, I'll now elaborate on this. So there's a little spoiler alert, right? So we will again use LPs at some point. We have some similarity to what we talked about before, to the operator counting constraints. We again use LPs to compute admissible heuristic values. But there are some important things that are different. And different both computationally and conceptually. So computationally, what we did in the previous approaches was we had an LP that basically specified constraints on, well, at the end of the day, on the costs of reaching the goal from a particular state. So we had an LP that we set up to compute one heuristic estimate, or at least that's the case for operator counting constraints. This story is slightly different for cost partitioning. Maybe there's a connection linking, lurking there too. We see that. But yeah, so with the potential heuristics, we have one LP that we want to solve, and that will actually define an entire heuristic function. So not an estimation for one state, but a function that we can then apply to every state. And that is very neat. That's very nice computationally, of course, because we only have to invoke the LP solver once, and it really doesn't come for free. I mean, it's not always prohibitive, but doing it once is definitely nicer than having to do it a few million times. So we not talk about runtime data much here, but if you stay until the very end of the conference, you'll see some very nice speedups actually lurking behind this slide. And that's kind of on the computational side, but there's also something very different, very interesting here conceptually, kind of regarding how we actually approach the problem of heuristic design. So in a way, what we're trying to do with the potential heuristics is not to say, okay, here's an idea, here's my heuristic, you know, let's kind of, this is what I want to do, let's work out with pen and paper what's going on here. We're kind of trying to shift the burden of doing that to the computer. We're kind of going a level up and kind of being a bit more axiomatic, and we're kind of saying, you know, here is what I want heuristics to be like. Like, I want heuristic to be admissible. I want heuristic to be consistent, and this is of course kind of the magic ingredient. This is what I want the heuristic to look like mathematically. I want it to be a linear combination of features. This is what I want. Now, you know, I'm the human, I've done my part, you're the computer, give me the heuristic. So we really don't say, this is the abstraction I want, this is how to compute the value. We just basically specify the properties we want to have, and then the problem of actually finding the heuristic is an optimization problem that we delegate to the computer. Now, that may be a bit abstract at the moment. We see how we can actually do this in practice. Okay, so before I go into the details, let me again advertise a few presentations. So this idea was introduced this year at a AAAI paper, and basically this provides the background for all the follow-up work. So this is basically where the potential heuristics come from, where we kind of have the theoretical results and so on, and this is what we will mainly present here. Since then, there has been a bit of follow-up work that will be presented at this conference. So we get some very nice computational results that build on the previous ideas and show that you can be really, really fast with this kind of approach, and that will be a presentation by Jendrik Seip in the joint ICAPS SOC session. So this is the last session of the conference on Thursday. And also, this is something that Florian mentioned previously when he said, you know, it's enough to talk about operators whose precondition variables are the same as the effect variables. This is not just a little technical thing. There's actually something very interesting going on there conceptually that can be exploited more widely, which is also important for potential heuristics. And we also have a paper on that, a short paper, and that will be presented also at this ICAPS by Florian on the first day of a conference. I think we've already pointed that out too, yes. Okay, so what are these potential heuristics? So I kind of said it already, but let's take a bit more time to go through it step by step and fill out some of the details. So I will, a feature, I could call it a state feature if I wanted to, you know, have a longer, more descriptive description, but let's just call it a feature from now, because we're going to use the word a lot. So a feature is just a numerical function defined on the states of the task, like, you know, how many packages are there in this location, or even like just 1-0 variables, like am I broke or do I have some money? That's a numerical function defined on states. Now, and the potential heuristic for a given set of features is a heuristic function which is a linear combination of these features. So I could have 3 features, right? And for example, the heuristic that just sums them up, that's a potential heuristic. Note though, we often kind of have this impulse to just add things up, right? But we can also subtract things. So these can be negative numbers as well. So I can have 3 features and say, I want f1 minus f2 plus 3f3 or something like that. That's a potential heuristic. And actually one major source of inspiration for all this work was looking at the evaluation functions that people use for classical board games like chess, where actually they have used linear combinations of simple features like this since forever. Maybe if you play a game like chess, you might know some rules of thumb that say, like, you know, if I have a rook, it's worth 5 points. If I have a pawn, it's worth 1 point. If my opponent has a rook, it's worth -5 points for me. That's just this kind of heuristic, and they've been used a lot in, you know, alpha beta search and so on, mainly for the reason that they're very simple to evaluate and also very, very simple to evaluate incrementally. Because if I go from one state to the next one, and I know some of the features don't change, then I actually can also incrementally compute this thing very efficiently, and that's another very nice property of this kind of approach. Okay, so that's kind of the general definition, but we'll be mainly focusing on particularly simple kind of potential heuristics where we use basically the simplest features we can think of. And this is basically, well, we call this an atomic feature. So an atomic feature simply tests if some fact, some proposition is true in a given state or not. And by fact proposition, I really mean something like, does this variable have this particular value, yes or no? Okay, so let x equal to x be an atomic proposition. Then this induces a feature, or this defines a feature f x equal to x, and this feature will have the value 1 in a state if I have x equal to x and 0 otherwise. So it's kind of like in chess, the only things I'm talking about, is there a pawn on square a4, yes or no? These are the kinds of features I'm using. And these are the only ones we consider now, but you obviously see there's actually potential for generalization there, right? So there's scope for like plenty more papers there. And okay, so what could a potential heuristic look like? So let's say we have two state variables, x and y. I could, for example, say, well, if x has a value of a, that's worth 3. If x has a value of b, that's worth 1/2. If it's worth has a value of c, oh, that's bad. Let's subtract 2. And if y has a value of d, let's add 5/2. Okay, this is heuristic function. Why is it heuristic function? Because it maps states to a number. It doesn't have to be admissible, right? So far, I know nothing about this other than that it's kind of defined in a certain mathematical way. So how do we come up with a good potential heuristic, one that actually has nice properties? Well, so what does good actually mean? Well, often, especially, we said at the start, we want to be optimal. So if we want to be optimal, we want to be admissible. Let's say we want to be consistent for good measure. That's not really necessary for optimal planning, but it's sometimes useful, and it turns out to be quite easy to achieve in this case. So let's say we want an admissible and consistent heuristic. That's not enough, though. I can give you a very nice, well, not that nice, but a very simple to find admissible and consistent potential function heuristic, f equals 0, right? That's a linear combination. What it's missing is actually having some sort of correlation with the actual goal distance. So we also want it to be well-informed, whatever that means. That's a bit fuzzy, like close to H star. Okay, so how can we achieve this? Well, that's where we have the linear programs again. So the very nice property of these atomic potential heuristics is that we can write down a set of constraints on the weights that exactly characterize which of these functions are admissible and consistent. So maybe let's take a step back. What actually is the problem we want to solve? Once I've fixed the set of features, the remaining thing is only to assign the weights, right? Finding a potential heuristic boils down to coming up with suitable weights. Some weights will give me admissible heuristics, some won't. So the question is, which combinations of weights will give me admissible heuristics? Well, what you usually do if you're faced with a problem like that is kind of trying to come up with some kind of sufficient criterion. Like if my weights are like that and like that and that, then it's going to be admissible. And then next year you write a paper that says, actually I can relax it a bit, you know, this is a case where it will also be admissible. Now we won't have to write the follow-up paper in that case, because this already completely answers the question. This is a characterization. So if I want my heuristic to be admissible and consistent, then I have to satisfy these constraints. And if I satisfy these constraints, then my heuristic is admissible and consistent. Why is this the case? Because the constraints are actually quite direct from the definitions of these properties. And to see this, well, there's a slight detour there. So we know that a heuristic is admissible and consistent. Actually, if it is consistent and has a simpler property, namely being equal to 0 in the goal state, right, in the presence of consistency, this is actually enough for admissibility, and the other way it works too. Admissibility gives you this. So it's enough actually to have goal awareness and consistency. And these are actually things that are very simple to write down for these kinds of heuristics. So for example, goal awareness, the heuristic value equals 0. Well, how do you write a constraint that ensures that? Well, we know what the heuristic value of the goal state is. Well, let's assume we only have one goal state. We know what the heuristic value is. It's just the sum of weights of all the facts that occur in the goal state. And if that heuristic value should be 0, well, then let's write down the constraint that these weights should add up to 0. Very easily done. There's a problem here. Usually we have more than one goal state, right? What do we do then? Actually, this is where this normal form that we talked about a few times now, that says, you know, you can actually restrict attention to planning tasks of a certain form, and that's not going to destroy your heuristic, and it's not going to be expensive, again comes to the rescue. Don't want to talk much about that, because again, this will be covered by Florian's talk in a few days. So we can assume that we only have one goal state, and then we just write down this constraint which says the heuristic value of that state is 0. Now, how about consistency? Consistency is basically about how does the heuristic value change going from one state to the other. And for this kind of heuristic, well, we actually know how the heuristic value is going to change. Basically, all the features that we lose, they will kind of lead to a decrease of the heuristic value, or they will get subtracted from the heuristic value. All the features that we get from the operator will be added to the heuristic value. And those numbers, like, you know, those are directly encoded in the constraints. So the only thing we need to ensure is that, well, the weights of all the facts that are consumed by the operator in the sense that Florian talked about, minus the sum of the weights of the facts that are produced by the operator, do not exceed the cost of the operator. This is necessary for consistency, and it's also sufficient for consistency. So if it's consistent, it will satisfy that. You just have to kind of move this to the other side and kind of add the sum for all the things that stay the same between the two states, but they will balance out. And on the other hand, if this is not satisfied, then it's not difficult to find a state for which consistency is violated. It might actually be an unreachable state. So we are kind of actually being consistent here in all states that one can write down. It's possible to be a bit more strict there, but let's not spoil our nice theory here by saying you can do better by being paying a bit more close attention to reachability. Okay, so this basically says I have a very, very clear handle on what are the admissible and consistent potential heuristics. It's exactly the ones that satisfy these properties, and you will note that these are just linear constraints, right? This is a linear inequality. This is a linear equality, which can be written as two inequalities, less or equal to 0, and at the same time greater or equal to 0. So this is kind of almost a linear program. What is missing yet is the optimization function. And because the optimization function is missing, I can optimize whatever I want. And this is basically the part that will help us find a well-informed potential heuristic. So what I have now is some constraint that kind of describe a space of heuristics. Everything that is kind of feasible for these constraints will give me an admissible and consistent heuristic. Now I get to pick one, and the way I get to pick one is kind of to guide the LP solver towards the ones I like. And I can do that by encoding the quality metric I like in the objective function. And of course, there's like a little restriction there. I can only do that if that objective function can be expressed as a linear combination of the weights, right? Because that's the variables you're using here. But fortunately, for many of the things we like to optimize, that's actually very easy. So for example, it's very easy to write down as a quality metric the heuristic value of a particular state. Let's say I want to find the best possible potential heuristic, the one with the highest possible value in the initial state. Very easy to do. I just basically use the heuristic value of the initial state, which is just the sum of the weights of the facts that occur in the initial state, as my optimization objective function, and then I ask the LP solver to maximize that. It will give me the best, or there can be multiple, so one of the best heuristics for this initial state. But I don't have to stop there. I can take 100 states, sum them all up, and then I will get another quality metric, and that will give me the heuristic with the best average value, essentially, over this set of sample states. I can even do something more complicated and say, actually, I want the best average value about all states in the state space by kind of realizing that I can write this down in some kind of linear metric too. But I should really stop there, because then I would spoil Jendrik's talk, which will be about that. The point is we're very flexible there, and we can do quite interesting things there, but just by playing around with the objective function. Okay, so this sounds kind of nice, but it's still so far only quite loosely connected to what we talked about before. The main connection is that we're using linear programs again, but I mean, many things can be written down as linear programs. It turns out there's actually much tighter connections. So what does this have to do with what we talked about before? Well, it turns out that it's really the same thing we've just seen. So what does this say? Let's take a state, and let's take the best possible potential heuristic for that particular state. So we have a large state of admissible and consistent potential heuristics, and each of this assigns a particular value to the state. Let's take the best one, like the best thing that this approach can give us. Well, it turns out this is actually just, again, exactly the same as the state equation heuristic for that state, and it's exactly the same, because that's what Florian showed, as doing the general optimal cost partitioning over the atomic abstractions for this particular state. So it's really the same idea showing up again. And how do we prove that? Well, basically by looking at the LPs, as you always do. In that case, one way to start is by looking at the state equation heuristic, producing the dual of that, and then seeing, oh, actually that's essentially, with some reformulations that are kind of equivalent, essentially the constraints I arrived at here. And this is the interesting thing is we kind of stumbled over this completely by accident. Like ages ago, we thought about this idea. Why don't we come up with these heuristics that are kind of introduced in this declarative way? Maybe they're good, Let's write this down kind of as a working note. Maybe we'll think about it a bit deeper when we have more time for it. But let's focus on other stuff for now. And then a few years later, we we came up with this, or we looked at the state equation heuristic, and after a while doing this LP thing, you're kind of trained almost as a reflex. Whenever you see an LP, look at the dual. Does it mean anything? And if yes, can you extract any information out of that? So we looked at it quite closely and said, oh, hang on, those are actually these potential heuristics from our notebook. So that was, to us, quite an unexpected connection. But like many of these things, actually, the more you think about it, the more it makes sense, and the more you can kind of build bridges between these various approaches. Okay, so this is basically the take-home message from this. So we've seen that, in a way, the general cost partitioning, which is just, your like last year's old-fashioned cost partitioning, but only with these additional negative values flowing around, right? On the one hand, then all these operator counting constraints that kind of are cropping up all over the place in planning these days. On the second hand, and running out of hands, the potential heuristics, they're really kind of different ways of looking at the same underlying phenomenon. And you can kind of view this as a bad thing. You try to come up with lots of ideas, you always end up with the same thing. So that's kind of bad in the sense that the same thing is certainly not better than what you had before, right? But really every time you look at it, you're looking at it from a different angle, you see things you didn't see before, and it helps you improve the things that you worked on before. That's certainly what we found. For example, one very nice way, I hinted at that already, is because this is so fast evaluated, it basically gives you a fast admissible approximation for the state equation heuristic. So what the theorem said is the best possible potential heuristic for every state, if you do that, then you get the state equation heuristic. But of course you don't have to do that. You can just pick any state equation heuristic with an objective function you like. That will be, if you use a good objective function, close to the state equation heuristic, but it will be trivially easy to compute. You don't have to solve an LP with 1,000 variable. You have to compute a linear combination of 1,000 things you can look up in constant time. And actually, in normal form, you can actually compute the heuristic value incrementally in constant time. And also, one thing we always want to do is take the state equation constraints and put on these combinations of facts, or do the optimal cost partitioning over atomic projections and then extend it to larger projections. And usually we kind of fail doing that because things get messy and complicated quite quickly. And not necessarily in theory, but then in practice you realize, okay, once you move from all the variables to all the pairs of variables, it becomes very expensive. So you have to start making compromises. And then it really gets messy. This view with the potentials, at least I feel, gives a very clear and clean way of trying to extend things like that in a kind of selective way. Let's take these atomic features. Let's look carefully at kind of what is going wrong with the kind of abstract solutions that correspond to what I'm computing here. Let's selectively add some features that seem to be relevant, and let's see what happens. And that's, I guess, a clear path towards generalization, so that I guess translates to our plan for the next paper, right? So I won't encourage you to work on that, but please work on everything else. This I think is a very very interesting way of looking at the different heuristics. So in the previous tutorial, if you were there for that, we had this kind of set of research ideas at the end. We're not really putting this up here because it's almost pointless, because it's really so easy to come up with interesting new results that everything I write down today will kind of already be done by someone tomorrow. I'm kind of exaggerating a little bit, but this is really, we feel that we've kind of opened the door, and there's this things there like everywhere that you can do. It's pointless even to point them out individually, because just look at these things and it will hit you in the eye that there's lots of things you can do there. And I think this is what we want to conclude with. We actually have some annotated bibliography at the end as well that we will talk about briefly, or that Gabi will talk about briefly if interested. But before that, we'll also take your questions if you have any questions about this. So thank you for your attention.
I can keep it briefly, just to give credit to those who actually did the work we presented here. So let me first go back to the optimal cost partitioning. So this optimal cost partitioning for abstractions goes back to Michael Katz and Kamil Domschlag. And now I say, you see, you can optimize this and get actually the optimal cost partitioning. But back then, many people tried to come up with good strategies to find cost partitionings, and then these guys came and say, well, you know, we can do it in polynomial time and do it optimal. So that was really a big surprise back then. The cost partitioning for landmarks goes back to Erich Karpers and Kamal Domschlag, and in their paper they have a slightly more complicated, or actually more intuitive version, which uses lots of unnecessary variables. So what I showed here is like a slimmed version, which is slightly more efficient to compute, and it's nowhere published. So it can be traced back in the code of Emil Kaider, Silvia Richter, and Malte Helmert. The the dual I showed you, which is more intuitive with the number of occurrences of operating the plan, goes back to Bleibonet and Malte Helmert and strengthen landmark heuristics via hitting sets. Okay, so for the operator counting, the frameworks was introduced in 2014 by us and Bleibonet. The post hoc optimization can be found in this paper. I just go very quickly because we are quite at the end. That's more interesting. Florian commented only very quickly briefly on this LP formalization of relaxed planning. If you're interested in that, you can find the details in the work by Tatsuya Imai and Alex Fukunaga. And this is like main message here. There is a very interesting paper in this conference. It's Outstanding Paper Award by Toby Davis, Adrian Pierce, Peter Stuckey, and Neil Lipovetsky. And this is on this sequence and operator counts, where they actually try to get information from what the variable values of the solution of the LP, and really get information from this, try to sequence this and improve the LP. So very interesting. I can highly recommend that. State equation heuristic is also part of the previous slide, but I collected it here. It was originally introduced by Menkes van den Brilche, Benton, Rao, Common Party, and Thomas Vossen. By some reason, this work didn't get the attention it deserved and was rediscovered from a different angle by Bleibonet. And they joined forces last year and introduced this dynamic fluent merging into this state equation heuristic topic. Okay, and then this very last topic Malte talked about. If you're interested in the details of this general cost partitioning, potential heuristics, or the connections between these three concepts we introduced or spoke about, have a look at this paper, which appeared at AAAI this year. And another teaser, more advertisement. If you're more interested into these potential heuristics and what are good or interesting quality objectives, go to the talk by Jendrik, which is in this conference. So I hope that's it.